Thank you for introducing me. And also, I want to thank the organizers for inviting me and giving me the opportunity to talk exactly about that, the Anomalous Hall and Anomalous Nernst effect. You're already kind of spoiled in the cobalt tin sulfur. The Anomalous Hall will be large, but there are still some interesting, details, not so much of quantitative nature, but of qualitative nature, which I want to elaborate on. And the talk will be mainly experimentally, so I will focus on if someone thinks, oh, that's a nice material, let's measure the Anomalous Hall. How do you design your experiment? What are the issues, the complications? What are your limitations? Just so there will be a lot of pictures. To begin with, I would like to thank all the collaborators who contributed to that work. So that were people from the IFW, the group I'm working at. Also, a very important collaborator is the group from Sebastian Gönnwein at the Technical University. And the crystals were supplied by Claudia Felser's group from the Max Planck Institute. All right, we already heard today that there is a quantity called Berry curvature. And back in the 60s, no 50s it was, people already figured that this term will give an anomalous transverse velocity to your electrons. So if you have a material which has a Berry curvature or which has a large Berry curvature, you will expect a transverse transport response. And we already saw before also there is a rather simple formula how you can actually calculate the Anomalous Hall conductivity out of that. And what you do is just you integrate the Berry curvature and the Brion zone over all bands which are occupied. And with that you would get the intrinsic Anomalous Hall conductivity for your material. That per se, as I had to learn this year on the March meeting from Said Hassan, has nothing to do with topology, and that's right. There is no topology in there. But in many topological materials, you will have a strong Berry curvature because the Berry curvature is related how your wave function changes with the k-space. So you have in materials which have, for example, Weyl points or the nodal lines, you will often find a very large Berry curvature, which then results in the fact that if people report large transport responses, that are usually the so-called topological materials. And that brings me to the material I'm looking at, so a little bit more detail. The cobalt tin sulfur consists of also Kagome lattices formed by the cobalt atoms. And these layers are stacked along the C direction. So you have one layer here, another one here, here, and there. And in between you have the tin and sulfur atoms. The compound, if you look at the magnetization versus temperature curve, is paramagnetic at room temperature or at 300 Kelvin. And if you cool it down, it will start around 175 Kelvin to order magnetically. I put the ferromagnetic up here in parentheses because right now there is a discussion ongoing if it's purely ferromagnetic or if you have a contribution from some in-plane antiferromagnetic order. But for the picture I'm drawing, I simply assume it's a ferromagnet, so the cobalt moments will be pointing along the C direction. And this is what you also see if you look at the magnetization versus external field. So you apply an external field along the C direction, so that are the curves out here. And you see that you have a sharp switching around the zero field. So if you apply a magnetic field, magnetization will be out of plane almost immediately. And if you apply a little field in the other direction, it will flip. And you can see that if you apply a field in plane, it is very, very hard to rotate the magnetic moments into plane because even the 7 Tesla you have here are not sufficient to saturate in plane for the 150 Kelvin. And for the 2 Kelvin, it's even more complicated. So there you will need more than 20 Tesla to saturate. And that is rather important if you think about the geometry. You want to measure the Anomalous Hall response because you will have a cross product of the magnetization, the electric field, and the other direction will be your response. So if your magnetic field would be collinear with your electric field, you would not get the transverse response from the Anomalous Hall. Okay, the band structure of the cobalt tin sulfur looks like that. If you do not include spin orbit coupling, and you have between the U and L point you have this crossing on the high symmetry line, and you have another crossing between the L and gamma point. And this, if you look in the 3 dimensions, this will actually form a nodal line. But if you include spin-orbit coupling, that will split. And if you cut in another, not arbitrary direction, but not straightforward direction, you will see there remain 2 ungapped points. So you have 2 Weyl points, or a pair of Weyl points. And actually in the Brillouin zone, you will have 6 pairs of Weyl points. And in the beginning, I motivated that such features are related to a large Berry curvature. And if you have the band structure, you can simply calculate your Berry curvature and map it. This is how it looks for the cobalt tin sulfur. Oh, I thought they only cut the logo, but actually they also cut all my the literature, so the references, which is unfortunate because that is, for example, taken from the paper from Enke Louis out of the Nature paper. And you can see this is the Z component of the Berry, or the blue indicates the magnitude of the Z component mapped onto the YX plane. And, oh, damn it, yeah. You see that is the position of the nodal rings, or the nodal lines, which would be there if they are not gapped. And the dots are the Weyl points. And if you now cut in the Y0 plane, you can see that around the Weyl points there's a large accumulation, but actually the biggest accumulation comes from the gapped nodal line out here. And if you then do this calculation, you can get the expected anomalous Hall connectivity as a function of the position of your Fermi level. And at the charge neutral point, you get something like a little bit more than 100 Siemens per millimeter. Since we heard before it is over 1,000, if you go to Siemens per centimeter, that would be something like 1,000, 1,100 Siemens per centimeter. Yeah, so that's what we would expect. And we heard in the talk before that if you want to apply this material or any material to technology, you will have to fabricate it in thin films. And unfortunately for this material, there's only one group in Japan who has reported so far the successful growth of that material. And all other groups are working on single crystals. And single crystals are a little bit tricky for transport experiments because you have to take care about where is your current flowing and about the geometry. So that is non-trivial, I would say. So we have a different approach. So we start with the single crystal, which looks like that. So the cobalt tin sulfur actually grows in such hexagonal shaped flakes. And we then use focused ion beams. So we just bombard the sample with ions. And you can use that to really cut some shape into your material. And we cut a beam out of the material. And actually you can see here and back there where we already cut a beam away. And you can then pick this up, which is typically 50 microns long. You can make it 5 microns wide. And the lower limit is something like 200 nanometer. If you make it thinner, the ribbon will start to bend and you can't cut it anymore. So you can pick this ribbon up, put it on a different substrate. And this is super nice because after that we can do lithography. So we can fabricate very, with high accuracy, we can define the contact. So we don't have, or we are very sure that in the middle, that's the cobalt tin sulfur. If we drive a current along here, that the electrical field will be more or less homogeneous, more homogeneous. And I said in my title that I also want to look at the Anomalous Nernst effect, which is somehow the thermal equivalent of the Anomalous Hall effect. So instead of driving the electrons with an electric field, you apply a temperature gradient, which will result in the movement of the electrons. And for that, we have the on-chip heaters here, so we can create a temperature gradient just by driving a current through one of the heaters, and which is very complicated. We need to evaluate the temperature gradient, which occurs over the sample, and that is why we need the thermometers on both sides of the sample. Coming to the Anomalous Hall effect, pretty simple. That is mainly a figure for myself because you always have to keep track of polarities. Because if you don't lose that, then your science will be horrible, or it will be a mess. And we just drive a charge current along the ribbon and pick up also the longitudinal voltage and the transverse voltage for the Hall while applying a field out of plane. And this is how a typical Hall sweep in this material looks like. So you see there is some linear slope in the back, which is just ordinary Hall. and you have some sharp switching around zero field, which is the anomalous contribution. And you get that out because you see there is some S-shaped behavior here by extrapolating the high field part back to zero. And since the Hall effect is an off-diagonal element of the tensor, you can just anti-symmetrize the positive part and the negative part to get the overall anomalous Hall resistivity. And that is what is plotted here. So you see in the paramagnetic regime, you have no anomalous Hall effect at all. And when it's ordering and even a little above, where the susceptibility of the material is large, you get a steep increase, reaching a maximum, and then decaying afterwards again. In the previous talk, it was already mentioned that when theoreticians calculate anything for the anomalous Hall, it is always conductivity. So theoreticians talk in conductivity, and experimentalists talk in resistivity, because resistivity is way easier to measure. And if you want to look at conductivity, that is, if you directly want to measure conductivity, this is very complicated. So what you have to do is, so that is actually how you would write it down. Your charge current is the result of your conductivity tensor times the electrical field. And you can just, if you replace it with the resistivity tensor, you find equations how you can, if you know the longitudinal resistivity and the transverse resistivity, you can calculate the conductivities as well. And if you now plot the transverse conductivity, so the anomalous Hall conductivity as a function of the longitudinal conductivity, you see that it reaches a plateau of somewhere like 95 Siemens per millimeter, so 950 Siemens per centimeter. And this plateau-like behavior is what you expect for the intrinsic anomalous Hall effect, because it does not depend on the scattering events in your sample. And if you now compare that to the calculations, you see there is a quite nice match. Of course, there are still 10% in between, but this is due to the fact that also in our very defined geometry, getting all the dimensions is very hard, because you measure voltages, so you have to get to resistivities, you need the thickness, the length, and everything, and there you can make, especially in the thickness, you can make mistakes. And there's another quantity, which is kind of the conversion efficiency. So always if you have a transverse effect, you divide it by the longitudinal, for example, conductivity, and this gives you the conversion efficiency, and you can do the same for the anomalous Hall effect, which is then called anomalous Hall angle, which is this conductivity over the longitudinal conductivity. And you see that for all materials plotted, the cobalt tin sulfur is somehow an outlier, because it combines a very large intrinsic anomalous Hall conductivity by itself, and also the efficiency, how you convert it, is very high in that material. Now, coming to the second part of my talk, the Anomalous Nernst effect. There's a very nice paper, again it's missing, from Noki from 2008. That's where the graph is from. And he plays with a very simple toy model, just 2 Weyl points, and looks at the Berry curvature, so that's zoomed into that area down here. And you see that the Weyl point results in roughly such a shape of the Berry curvature. And if you now want to calculate the anomalous Hall conductivity, you will have this prefactor, this weighing function, which is shown here in blue. So you will take all the states, all the occupied bands, or we will take all the occupied bands. And if you calculate that and you switch, or if you shift the position of your Fermi level, you will see that the response function looks something like that. So if you're, for the anomalous Hall, positioned exactly at the level of the Weyl points, you will get a huge response. And now the interesting fact is that for the anomalous Nernst conductivity, the weighing function is somewhat different. So instead of taking all the states below the Fermi level, you just look at the states around the Fermi level. And if you now again plot the response as a function of where your Fermi level is, you see that if you would be exactly at the Weyl point, you would get no response at all. But therefore, if you're somewhere away where the anomalous Hall conductivity is already decaying or being smaller, you can get a huge response, and that below the Fermi level and above the Fermi level. So in principle, this could be used to study different states in your material, as you would have access to with the anomalous Hall conductivity. Now, how does that look experimentally? This is way more difficult than the electrical transport, because for the electrical transport, you just take some source meter and drive a current, but there is no machine driving a thermal gradient. That's why you have the hassle with the ohmic heaters, so the the current heaters I have shown before. And what we do is to evaluate the temperature gradient. You've seen the thermometers we have. So we just measure the resistance of the thermometers as a temperature of the cryostat. So at the end, we know exactly if the thermometer has that resistance, it's that temperature. I mean, it's like a basic thermometer. And if you then heat one side, this is shown here, so you increase the heater power on one side, you will see that the resistance of the thermometers will increase. That's how you would expect it. And you can see that one side is heating up more, the other one is not heating up that much, so you have a temperature gradient at the end. And we just assume the temperature gradient to be linear over our sample. That is some limitation because we don't know it any better. And evaluate the temperature gradient at the end like that. I've shown before that the linear response in the absence of a thermal gradient, so if it's isothermal, will be just the conductivity tensor times the electrical field. But if you have a temperature gradient, you get this thermal power tensor also there. Again, measuring current is super difficult, so you will measure electric field voltages, which means you have to transform that equation into the case where J equals 0, and then you will have this combination of two tensors, and that is your actual transport response. So if you do the transport experiment, you cannot access the thermal power directly, but you will have the combination of those two tensors, which we then call the Seebeck tensor. And now we can do the same game again. We just record the longitudinal or the transverse response and get the different parts of the Seebeck tensor. If you do that for the Anomalous Nernst effect, you see a qualitatively very similar behavior. So you have some linear background coming from the ordinary Nernst, and you have some switching around zero field, which comes from the Anomalous Nernst. And I also evaluated exactly the same way. So I extrapolate to get the actual value of the Anomalous Nernst coefficient. And you see already from the raw data, there is some qualitative difference. And that is that if you change temperature, your step changes from a positive step to a negative step. And if you plot that, this becomes more clear. So in the paramagnetic state, it's zero as you would expect. And when it becomes finite, it takes positive values and afterwards changes sign and goes to negative values. And if I now compare that to the temperature dependence of the Anomalous Hall resistivity, this looks significantly different. So I was like, oh yeah, nice. I wanted to look at two different effects which look at different states. This is exactly what I want to know. But what do I do with it? You need to be careful. The model I showed before, again, is only for conductivities. So that is not valid for resistivity, so it's not so straightforward to say anything from that. But nevertheless, it was puzzling to me that you can get a no sign change in the Anomalous Hall, but a sign change in the Anomalous Nernst. So I did some literature research, and there is one paper from Pu in 2008. And he looked actually at the Anomalous Hall and Anomalous Nernst in gallium manganese arsenide, and he sees exactly the same. So he has some positive, let's call it positive Anomalous Hall effect, and he has an Anomalous Nernst effect which switches sign in between while the Anomalous Hall effect stays constant. And what they do is they look at the Mott relation listed here, which is relating the Anomalous Nernst conductivity, so to say, with the Anomalous Hall conductivity. And if they just assume a very simple power law approach relating the Anomalous Hall resistivity and the longitudinal resistivity, they, after some calculations, they come up with an equation relating the four thermomagnetic transport coefficients and they only require two parameters, which is this lambda prime over lambda, and the n comes from the exponent over here, and they take this to fit their data, and actually this fits quite well. So also the sign change is captured by that quite well. And they not only are able to get a fitting equation for the Seebeck, the transverse Anomalous Seebeck, but also for the Anomalous Nernst conductivity, and that matches as well. So I thought this is a very good idea to apply that to my material system. And as I showed before, since in the thermal power, or in the Seebeck, the thermal power is somehow mixed with the conductivity, you have to write down the tensors, and you will get this equation to formulate the actual thermal power or the Nernst conductivity from the Seebeck coefficients and the resistivities. Just as a reminder, this is collected how the different contributions scale over temperature. And if you do that, you get some anomalous Nernst conductivity looking like that. So this now, again, is very typical for any material you look at. So it's in the paramagnetic regime, it's 0. If it orders, it becomes finite and reaches a maximum. And since it's linked to the entropy, it will go back to 0 if you approach 0 temperature. And what I did then, I took the two fitting equations I described above, how the people got them, and just used them to describe my data. And okay, I have to be honest, that is not a fit, because if I let a fit try to get this, there will be some, so it will underestimate that, but overestimate that, so you will have a different shape. But if you manually choose that type of parameter, you can get it to match down here quite well. But you see that there is a huge deviation around the critical temperature. And if I now choose the same set of parameters, which should be valid in principle, to fit the anomalous Nernst conductivity, if you would just fit it and you look at it as an experimentalist, you would say, oh yeah, nice, that is matching, cool. But if you look closer and you calculate the difference between the data and the, this fit, you could say, you see that the leftover has the same shape. So there seems to be one contribution which is not accounted for yet. So we were wondering where that could come from. And our best explanation so far is that since the thermal transport is always related to the entropy, it's the fluctuations in the magnetic order around the ordering temperature, which results in a flow of entropy and thereby affects the anomalous Nernst conductivity. But we did not find any model for that or describing that so far. And with that, I would like to summarize my talk. So in principle, we were able to fabricate single crystalline microstructures of that material to access all the galvano and thermomagnetic transport coefficients. And the nice thing about this platform, you can say, is that if you have any other material only available as single crystal, you can in principle apply it and do the same transport experiments. We can actually observe the large intrinsic anomalous Hall conductivity, which is governed by the Berry curvature contribution as it is calculated. And we could find an additional contribution to the anomalous Nernst effect around the critical temperature, which might be related to magnetic fluctuations. And with that, I would like to thank you all for your attention.